Hey guys, so today I'll be talking about the concept of wireless power transfer. What is wireless power transfer, WPT? It's, as the name implies, it's the transmission of electrical energy without the use of any physical link. And one of the main challenges found in traditionally wired power systems is the loss of electrical power during transmission time. And these losses have even reached figures that are estimated to be around 26%, and they can primarily be attributed to the fact that the the resistance in the conductors used can be a little higher than expected, such as in wires, and consequently, this is where WPT comes to effect. There's numerous benefits to using these systems beyond eliminating the need for additional wires or batteries for support. Um, they're faster and more reliable. In terms of safety, these technologies also reduce the risk of electrical shock, among other hazards in environments. And so the focus of this report and this presentation itself will be on the basic functionalities of contemporary wireless power transfer systems and some other aspects that are being researched and developed. So, principle, how does it work? Essentially, this diagram doesn't exactly include all the parameters that come into play, but it pretty much tells you the idea of what's going on. In the illustration, you have a transmitting coil that's being driven by a high frequency AC current, which generates a time varying magnetic field. And through inductive coupling in both coils, the induced voltage in the receiving coil extracts the power and supplies it to the load. And this is just one of the many ways that um, power the that power transmission can be achieved. And in your transmitting and receiver ends, you would have pretty much an RLC circuit with each respective um, each respective parameter in each different um, receiving and transmitting end. And do you have the inductive coupling represented by the fields going in between the two coils of wire? And for field regions, um, there's two main regions where this technology can be classified, and they are near field and far field, which are each distinguished by the range of transmission power. And so near field is non-radiative since energy stays within a close distance of the transmitter, and it's typically used for short distances. And the main the main ways in which power can be transferred are through um, means of capacitive and inductive coupling. And far field is a radiative technique due to it dissipating more energy, and the coverage in this area is much greater compared to its counterpart. And the way to transfer energy is through microwave power and laser power. So for the near field technique, many of the applications primarily use inductive coupling as opposed to capacitive coupling because of the greater danger that's associated with electric fields. And magnetic fields, on the other hand, pose less of a threat to living things. And inductive coupling, as I mentioned before, was just passing an AC current through the transmitting coil and creating an oscillating magnetic field with a voltage induced in the receiver end. And once that AC current is in the receiver, then it will either drive the load directly or be rectified to DC. And capacitive coupling follows a similar concept. However, now we're in the electric domain where the electric field is generated between the metal plate electrodes. And for the far field technique, um, these systems can achieve much greater ranges and distances. And microwave and lasers are the two main mechanisms of electromagnetic radiation that allow for this transfer to happen. And with the former, the microwave power transfer transmits in this case, the transmitter converts DC power to microwaves, and this transmits the microwave radiation to a target, which then in turn is converted back to DC. And so in the transmission stage, the microwaves are generated primarily with a magnetron, which is where the electrons are passed through a magnetic field. And then the continuous emission of microwaves from the transmitter is then extracted by a silicon control rectifier on a rectangle with the purpose of converting the microwaves back to DC. And in the latter, the laser power transfers are based on the sets of principles laid out by the photoelectric effect. And in this system, the transmitter converts power from a common source into a monochromatic beam of light via laser, which is then shaped with a set of optics and directed to the photovoltaic receiver. And while in the receiver, the specialized cells matched to both the laser wavelength and the beam intensity convert the laser light back into electricity. And so one of the areas that I was interested when I was doing this research was WPT efficiency, and there's numerous uncertainties that affect the parameters of these systems. For example, with regards to electrical vehicle systems, the mutual inductance depends on the vehicle's position itself, and also when charging these vehicles, the equivalent impedance of the batteries can also change, and as a result of these changes, the transfer efficiency of these systems will be changed as well. And so this requires techniques in order to track the certain operating points. And the most common method that I found in recent studies was to introduce an active rectifier and a DC to DC converter to the system. And this helps by regulating the output voltage of both the active rectifier and its phase shift angle. And so this can achieve maximum efficiency throughout different variations in mutual inductance and other loads. And one more thing worth noting is that these systems are assumed to operate at resonant frequency, and in that case, the active rectifier would act as a synchronous rectifier. And in the case that the operating frequency does deviate from the resonant frequency, then the active rectifier would then be able to cancel the reactive component in the system when using the generic or common method. And at the same time, the system would regulate the resistance component and would be able to ultimately track the optimal load. And one other area which I found very interesting was by implementing an intermediary coil in between the transmitter and the receiver. And the goal of this is to improve the transmission distance, meaning that a longer transfer distance can be achieved. But adding an extra coil in the free space between the transmitter and receiver is a bit inconvenient. So, like if you're considering a vehicle, it's pretty challenging to place another coil that would essentially be in between the air gap from the ground and the bottom of the vehicle. And to prevent the possibility of this occurring, you can just place an additional coil either like adjacent to the transmitter. And as long as the crucial characteristics of this is to increase the mutual inductance between the receiving resonator and the transmitting resonator, and to shift the current stress from the source coil to the transmitting resonator, then the present source loss is decreased, and this would benefit the system as efficiency would increase. And this would only happen if the transmitter is composed of those two inductively coupled coils that are installed close to one another. And that is pretty much my area of research that I did for this project. I also looked at two other areas of research that I focused on, that I covered more about in my report. It included multi-frequency WPT and bidirectional WPT, but due to timing constraints, I'm going to save that for another time. Thanks again for having me, guys.